All right. Well, my name is Elise van der Pol. Thanks to the organization for inviting me. I'm going to be talking a little bit about geometric deep learning in the context of reinforcement learning. So I'm doing my PhD in machine learning at AMMI, which is at the University of Amsterdam, where I work on structure and symmetry in reinforcement learning. I'm currently also interning at DeepMind's multi-agent team, so I'm actually not in Amsterdam right now. Before my PhD, I did the master's in AI, also in Amsterdam, and I graduated on the topic of cooperative deep reinforcement learning in the multi-agent setting. If after the talk you're interested in learning more or you want to chat, please hit me up online. You can email me or contact me on Twitter or something. In the meantime, please feel free to interrupt at any point if something's unclear or you have questions. So before I get to the research part of the presentation, I want to give a quick introduction to reinforcement learning and specifically MDPs, Markov decision processes. I've adapted this from some slides from Shehan Wang. I've not assumed any reinforcement learning knowledge on your part. So if you do already know most of this stuff, please consider it a refresher, and it's only a part of the presentation. So if we look at the field of machine learning, we can kind of divide it into three different parts. So we have the supervised learning, the unsupervised learning, and reinforcement learning. And while they all sort of share and exchange techniques, they all have their kind of personal challenges, I would say. And I think reinforcement learning is really the odd one out here. It has a very different approach, and it also has very different challenges. For example, in supervised and unsupervised learning, you have static data sets that you're then trying to learn something from. Whereas in reinforcement learning, you have to figure out how to get the right data in the first place, which makes the whole problem a lot more difficult. Some examples of places where you could apply reinforcement learning are, of course, AlphaGo, which made quite a splash at the time. It's a reinforcement learning system that beats the world champion of Go at Go, which was super impressive at the time. And we thought this was an achievement that was supposed to be quite far away. So it's very impressive that that worked out. There's also, for example, work on autonomous helicopter flying, which if you have time to look at the videos, is kind of cool. But you can also imagine that it could be useful for robotics, like healthcare robotics, or maybe you want someone to help you in the kitchen so you don't have to cook for yourself. And finally, something that a lot of people are also interested in is stuff like autonomous driving. So in reinforcement learning, we tend to focus on sequential decision-making problems. So we have some environments that can be the real world, it can be a grid world, it can be the internet. It's just some kind of environment that we're acting in sequentially in order to maximize some long-term objective. So some key features here are the reinforcement learning that you try to learn to take the best action by trial and error. So you take some actions in the world and then you evaluate how good were those actions. The problem here is that your reward can be delayed. So let's say you're trying to navigate a maze, you'll only get like a positive reward at the end of the maze. And until you reach it, you won't know if the actions you're taking have been good or bad. Additionally, we might have to sacrifice immediate rewards in order to gain more reward later. So it's definitely a problem where you also have to take the future into account. So you have to do planning. So if we contrast reinforcement learning to a supervised learning setup, in reinforcement learning, we take our current input, for example, an observation that we have over the world, we make a decision, and then the next thing we see depends on the decision we made before. Whereas in supervised learning, if you misclassify your dog as a cat, that only affects your score, but it doesn't affect what you're going to see in the future. So it doesn't really do too much to influence your future decisions. So it's a matter of learning to do or to act versus learning to predict. So a typical reinforcement learning task that we look at simplified versions of a lot is we have some robot in a maze and it's trying to find the shortest route to the goal. So this is sort of a classic problem. If we already know a priori how to divide the states up into like small discrete iterable things, and we already have discrete actions like go left, go right, then we can apply classic planning algorithms to solve this problem. However, in real robotics, this is usually not the case. Instead of knowing exactly where we are, we usually have some kind of sensor sweep of the environment. Our actions are not discrete, nice, clean actions. Instead, we have something like move the wheel by this degree to the left or to the right, for example. So this is something where applying these planning algorithms is much harder. We can formalize these kind of decision-making processes as Markov decision processes. So that's just a mathematical framework to model sequential decision-making tasks. We have some environment that gives us some observation, a state of the world. In response, the agent takes an action. And in response to the action, the environment changes again, and the agent receives a new state, new observation, and a new reward signal. So yeah, you can call this a sequential interaction flow. It's a feedback loop where you're trying to make sure that over time, the cumulative reward is increased. Oh no. Okay, let me try this again. Okay, I'm gonna try this slide without full screen because apparently it's not working. So an MVP is a tuple that consists of a set of states. So those are just the states that the environment can be in, a set of actions that the agent can take, a reward function that maps from the joint state action space to some scalar reward. Now, the rewards could also be a vector if you're in a multi-objective problem, but that's far beyond the scope of this talk, I'm afraid. There's a transition function that for a given state and action returns to you the next state of the world, and this can be either deterministic or stochastic. And so can the reward function, can also be stochastic. And then finally, we have a discount factor, which will make life easier later on. So the reward function and the transition function, if we take them together, are what we usually describe as the dynamics of the environment. The goal in a Markov decision process is to find a policy that maps from states to actions. So the policy can also be deterministic or stochastic. In the deep learning era, we very often model it as a vector representing a distribution, and then we sample from this vector. So if we, let me just try if I can maximize it again. Is this working? Yeah. So if we go back to the robot in the maze example, then in this case, for example, the states would be all the possible locations that the agent can take in the maze. The actions would be rotate the left wheel by so many degrees. And the reward might be, okay, we get 0 everywhere, and then we get +1 when we solve the maze. There are some assumptions that we make when we model some things as MVPs. So one is that the time steps are discrete. So we have like one action per time step. And the other one is that we're fully observable. So what does that mean? It means that the probability of the next state is determined only by the current state and the current action. So we don't have to take histories into account. So you would have partial observability, for example. Let's say you're a little robot driving along a corridor, and there's a bunch of identical doors. Then if you look directly at a door, you only know which door it is if you remember which doors you've seen before. So that's an example of partial observability. So we're interested in finding policies. And a policy is a function that represents the agent's behavior. So it's a mapping from states to actions, and it's very often modeled as a probability factor. So for example, in the maze problem, it would be something like, what's the route towards the goal that maximizes the rewards? And in order to take the correct route, we have to know what is the optimal policy at each state. So in order to determine which policy is optimal or which policy is better. Oh, I'm just seeing now, are there questions? Let's see if I can see them. Oh, you can hear me. Okay, that's good.
So maybe I can ask this. The full observability, is it in terms of the states or the actions or both?
Both.
Okay, thanks.
Yeah. Right, so if we want to talk about optimal policy, we first have to have a notion of how to compare policies, like which policy is best. So given this very simple grid world with some obstacles, oh, let's see, I'm not in it. Yeah, okay. So we have a blue route that goes like, we go to the right first, and we have a black route and we go down first. So the question is, which action should this robot take? So this is a question of which is the better policy. Able to, I think that whenever I put LaTeX on the slide, it's not letting me maximize it. So that's too bad. So we're going to do it like this. To measure how good a policy is, we need a notion of the discounted return. So what we're going to do is we're going to accumulate, we're going to compute the cumulative discounted rewards over time. So that's just saying, okay, we're in some time step, and then the cumulative return will be the reward that we get next, plus a discounted version of the reward that we get after that, plus a twice discounted version of the reward we get after that, and so on and so forth. So in this problem that we just looked at with the grid worlds, at every time step, we have a reward of -1. If we reach the goal, we have a reward of +10. And the discount factor for making computation easier, we now set to 1. This would usually be something like 0.9 or 0.99. So if we take as first the move right, and then we follow the rest of this route, or we take the move down and then we follow the rest of this route, if we compute the return, then we see that if we go right and follow the policy, we will get a higher return. So that would be the better policy to take. So this is just like, in a sense, this is just one sample of a return under this policy. If the policy is stochastic, or the transition function is stochastic, or the reward function is stochastic, this is not good enough to say which policy is better. So what we end up doing is we end up computing the expectation of the return under the policy. So what that just means is saying, okay, given that we have this policy, what is the expected return that we would get if we follow it from a given state? And that gives us the value of a state under a policy. We can also compute a Q-value function, which is kind of the same as a regular value function, except it's defined over state and action pairs. So we look at what is the expected return starting in a given state and starting from a given action, and then following the policy in the future. Okay, so let me try full screen again. Yes, okay. So how can we get good policies? I don't really have time in this presentation to go over the entire field because it's huge, but there's a nice overview that I think Herk van Hoof made. So if you know the dynamics of your environment and your environment is discrete and not too large, you can use dynamic programming algorithms such as policy iteration or value iteration. So these depend on just iteratively updating estimates of the value function and the policy. If you only have your environment and you can sample data from it, and then by data we mean state, action, reward, next state tuples, then what you can do is kind of two different things. So you can directly learn a function from your input. Like, for example, directly learning a value or Q-value function. So what you would do, for example, in deep learning is you would take your state, maybe that's an image of an Atari game, you push it through the network, and then you output either a Q function, or you directly output a distribution over action, so policy. And then you can just define a loss function that optimizes either the value function or the policy directly, And then it's just a matter of training your neural network. So if you're not interested in the deep learning part of it, you can also maybe use tabular methods. So you could use tabular Q-learning or SARSA, for example. Things like policy iteration, value iteration, and Q-learning and SARSA are very well described in Introduction to Reinforcement Learning by Sutton and Bartow, which I'll have on another slide if you're interested. If you're more interested in the deep learning part of things, then you can check out, for example, deep Q-learning, DQN, or reinforce and its derivations if you want to optimize your policy directly. And these are examples of model-free reinforcement learning. So they're model-free because we're not building a model of the environmental dynamics. So this gives you a hint. We can also learn a model of the environmental dynamics. And this can be a more data efficient way of dealing with the problem, because we can reuse the data both to update the policy and also to update a model. And we can use the model to update the policy as well. And this is what we call model-based reinforcement learning, not the most creative name. Do keep in mind that not all reinforcement learning can and should be modeled as a Markov decision process. So for example, if you have a multi-armed bandit problem, it kind of looks like a reinforcement learning problem, but your actions don't influence the states you see next. So it kind of means that you don't have to care about transitions, but you're still interested in finding the action that maximizes the cumulative reward. And you still have to come up with a smart way to try all the actions in order to be able to find a good policy. Another example is, as I mentioned before, partially observable problems. In partially observable problems, you have to reason about the histories that you've seen. This is classically done by considering something called a belief state, which is kind of a summary. I view it kind of as a summary of what you've seen before, but nowadays with deep learning, there are also stuff where they use, for example, recurrent networks to do this. And finally, multi-agent problems, if they're not fully cooperative, you shouldn't model them as MDPs, but as games. And if you're interested in this, then there's a book, A Concise Introduction to Multi-Agent Systems by Flosses, which I think is available online. I found it very useful when I was in my master's. So if you want to get started with reinforcement learning, then there are a few really nice resources online. There's Reinforcement Learning and Introduction. There's David Silver's course on RL, which I personally haven't really looked at, but a lot of people really like it. And then there's Spinning Up in Deep Reinforcement Learning, which dives a bit more into the engineering side of things as well. So do keep in mind that reinforcement learning is far from perfect, both as a field, but also as from the technical side of things. It takes a long time to train anything compared to sort of problems of comparable difficulty in, for example, computer vision. So you need a lot of data, mostly because the problem is just very hard with the future, taking the future into account and the long-term impact of every action that you can take. As a result, the methods tend to be very high variance and can also be quite unstable. And deep reinforcement learning is notoriously sensitive to hyperparameter choice, really in a way that something like supervised learning really isn't. If you want to see a little bit more about this, there's this paper called Deep Reinforcement Learning That Matters that I think lays out the problems quite nicely. Also, for example, in terms of what's the effect of the random seed on the performance of your algorithm, which is quite intense. Right, so before I move on to research, I think this is a nice point if you have any questions about the reinforcement learning part of things. No? Okay, all good. Then I will move on. So as I mentioned briefly in the previous slides, reinforcement learning is really data hungry. So a few years back, I plotted this, this graph where we take the number of samples for famous computer vision data sets. So we have MNIST, CIFAR, MS-COCO, and ImageNet. Of course, ImageNet is the biggest one. And then I plotted at the time a few popular model-free reinforcement learning approaches. And we see that this dwarfs ImageNet. So there's a lot of samples that you use to get any kind of good performance on, in this case, Atari games. But this extends to other difficult RL problems as well. Of course, this is a little bit of an unfair comparison because we don't know what computer vision people would do if they could sample new data all the time. And that's definitely the case in reinforcement learning. But I do think this illustrates quite nicely why this problem is far from solved. So what can we do? Well, I'm personally very interested in the observation that not every data sample that you take in reinforcement learning is unique. So I've shown here a few examples. So here we have a state in Pong, the Atari game Pong. And we have a similar, but quite different state in the same game. So if you take a naive model-free reinforcement learning approach, these two samples are not the same. So they're different samples. It's the same in the classic card pull control task. So you have a little card that drives left to right, and you have to balance a pole on top of the card. So you have to move the card just right so that the pole doesn't fall over. In a normal model-free algorithm, these are two different samples. It's the same for this little grid world here that I've drawn. It's just a grid world with a guy in a specific cell. And here in the blue version of the problem, it's the same guy in the same cell. But for a reinforcement learning algorithm, these would be very different samples. So I'm very interested in looking at things where we can exploit samples that maybe look different if you look at them naively, but if you consider the structure of the data a little bit more, you can actually gain a lot. And the way I do that is by looking at equivariances and invariances in the data. So you might already have gotten some lectures on equivariance and invariance, but I'll just repeat it here so that you know what I mean when I talk about them. So let's say we have a dog, that's our input. And we apply a transformation G, for example, rotation. Then if F maps the dog to latent space, if F maps the rotated dog to latent space, or F maps the original dog to latent space, we want there to be some equivalent G prime that's equivalent to the original G, such that we end up in the same space in latent space. So this is a commutative diagram that goes like this. So it doesn't really matter which route you take to get there, but you will end up in the same point. And this is equivariant. So we say f of gx is the same as g prime of fx. And this is an equivariance constraint that you see a lot in the equivariance literature. Invariance is a very related concept, except it's a little more strict. Well, maybe not strict, but it's just different. So we have the same idea. We have a dog, we rotate the dog, but now instead of mapping to a related point in latent space, we just map to the same point in latent space. And this is very useful for something like supervised learning, where you don't actually care if the dog is rotated, it's still a dog. So you want to classify it as a dog, regardless of rotation. In reinforcement learning, however, it's a bit more subtle. So if we look at this data, for example, this Pong, if we flip over the horizontal axis, then we're kind of at the same state again. However, if we take the same action, that's probably not a great idea, because here we need to go down and here we need to go up. So a flip of the input space also induces a permutation in policy space. It's the same for carpal. As we flip over the vertical axis, instead of going left, we now have to go right. So these are examples of equivariance in reinforcement learning. If we look at this grid world example with the little guy, then it's actually invariant under changes of color. So we don't actually care about the color of the state. We just care where the guy is in the grid world. So this is an invariance because the action doesn't change under the color. So I want to introduce the concept of an MVP homomorphism before I move on. I won't go into the technical details. You can look them up in one of Ravindan and Barto's papers if you're interested. Suffice to say that if you have An MVP, for example, in this case, we have a card pole which has a flip symmetry over the vertical axis. This is our original problem. So an MVP homomorphism is a map from our original problem onto a reduced problem. So in the reduced problem, we've kind of folded over the symmetries in the original problem. So what does this give us? Well, an MVP homomorphism preserves the dynamics of the original problem. This means that we can plan or, I don't know, learn a policy in the reduced problem, and then we can sort of bring the policy back to the original space and act optimally there. So that's very attractive if you can do that, because it means that you just save a lot of time by not having to go over all the symmetric versions of your data. Of course, it hasn't really taken off in the past, mostly because finding the MVP homomorphism can be quite expensive, and you need to know your environmental dynamics. Another example of what an MVP homomorphism would do, so let's say we have this grid world with a symmetry over the diagonal. What it would do is kind of fold over the grid world so that you only have to plan a route from the AB point to the goal rather than from A and B. Right. So for reasons of data efficiency, I've been very interested in model-based reinforcement learning. So why is that interesting? So I think if you're doing model-free reinforcement learning, you're actually trying to solve a very difficult problem. So you're learning a policy directly from the reward signal. What that means is you have to figure out vision. So what do different elements in the, let's say you have an image-based input, what do the different elements in the image mean? You have to figure out the dynamics. So how do the important elements change as I apply certain actions? And then you have to do planning on top of that to find a good policy into the future. And that's quite a difficult problem to do end to end. So what you can definitely do is find some good actions if you've seen something often enough, but it's not the most data efficient way to solve the problem, I think. So the advantage of model-free reinforcement learning is that we optimize for maximizing the return directly. The disadvantage is that it can be quite data hungry. So what we can do with model-based reinforcement learning is we separate the learning of the vision and the dynamics from the planning, which means we make the problem a little bit simpler. And that's a more efficient use of our data. But if you have a bad model, then your planning is also going to be bad because you're planning in a different MVP than the one you're actually trying to solve. So it's quite important to get a good model. So some people have been working around this by using, for example, model learning as an auxiliary loss for a model-free approach. So you can kind of sidestep the bad model part. Right. So I wanted to talk about this paper. We've called it Plannable Approximations to MVP Homomorphisms, and it's about considering equivariances on their actions of the MVP. So action equivariance can be a little confusing if you've already talked about group theory, because there an action means something different. Here we're talking about the action that you take as an agent in an MVP. So we're basically saying we're in some state, then if the agent takes some action, it will transition into a different state. Then if we map it to latent space, we should end up at the same point as if we map the latent space directly and then take an equivalent action. So this is again equivariance constraint, and this is again a commutative diagram. So what's nice here, if we enforce these action equivariance constraint, the network becomes a structure preserving map. And with structure preserving, I mean it preserves the structure of the original MVP. And we show for deterministic MVPs that this actually becomes an MVP homomorphism, which is nice because, as I discussed before, MVP homomorphism has some nice properties. Right. So we use these constraints in order to preserve the structure of the original MVP. On top of that, we also add a reward loss. So we're trying to make sure that the reward in the original state and in the latent state are matched. So this is also part of an MVP homomorphism. However, if your reward is sparse, meaning that you get no reward in most places except maybe a reward of +1 at the end, then this loss is not very informative, which means that this part of the loss dominates, and it's a really good solution to this loss function to just predict the same state everywhere. What we get is latent space collapse. So what we do to prevent this is take negative samples. So there's like contrastive loss or triplet loss, for example. Now, to evaluate the model, there are multiple things you can do. I was personally very interested in seeing if we can do exact planning in the latent MVP, just because exact planning doesn't really allow you to make mistakes in your representation. So what we do is we do a little bit of an ad hoc discretization of the latent space. Then we plan in the latent MVP with value iteration, so a standard dynamic programming approach. Then we evaluate the found policy in the original MVP. And this is nice because it allows us to evaluate the quality of the learned representations. So if we evaluate the learned representations in terms of planability, so meaning can value iteration find a good policy, then this approach trains in much fewer epochs than a baseline, for example, that uses a reconstruction type method. So you can see that here. So here we have a problem where the task is to get the key and deliver it to a corner. It's a very simple task. However, if you're training an autoencoder type approach on a given data set sampled from this environment, it takes a lot of time to get anywhere, mostly because it's spending a lot of time on getting good at reconstructing the states. So it has to train an entire decoder. However, if we take a different approach and we just take like negative samples combined with this MVP homomorphism loss, then the average episode length, so the number of time steps it takes us to solve the problem, drops dramatically and much faster. So I think this is a nice demonstration that this actually helps compared to autoencoders, which are still a little bit popular to use. We can also plan on cardpole, which is actually has continuous state space, but we can discretize it and plan with value iteration and actually get pretty good policies in only 100 trajectories. And we are also able to generalize over new image representations of the MVP and also to new reward functions and goals. And here we also plotted different representations learned by different approaches, where every dot is a state and the edges are predicted transitions and the color is the value function. So you see that an autoencoder is not so great at making like an intuitive latent space. So to wrap this one up, we're using action equivariance for learning representations in model-based reinforcement learning. This contrastive approach allows us to learn MVP homomorphism of the original MVP, which gives us better exact planning compared to reconstruction baselines or baselines that don't use contrastive coding. If you want to know more, just have a look at the paper. So the second thing that I wanted to discuss was the NERDS paper that we published last year, which is called MVP homomorphic networks, group symmetries in reinforcement learning. And here we go back to the earlier observation that there are symmetries in reinforcement learning problems. So for example, cardpole that we already discussed, pole, which has a horizontal flip symmetry, but also, for example, in a navigation task like a grid world, there's rotational symmetry, right? If we rotate the state by 90 degrees, then we turn the up action into a right action, for example. So we can write this down with another commutative diagram. So we say, okay, we take a state of cardpole and then we flip it with L, then compute the policy. And by compute the policy, I mean we push the inputs through a network and then output a policy vector. This should give us the same thing as when we map the policy space directly, and then we permute the left and right action with each other. So this is a commutative diagram and another equivariance equation. And it's basically saying that if you have a state action pair that is symmetric, like this state and the left action, or this state and the right action, then they should have the same policy phi. Now, if you write your policy down as a vector, then you can also see that computing the policy of the flipped state is the same as permuting the policy of the original state. So what we do here is we call this an MDP homomorphic network because it's an equivariant network that enforces an MDP homomorphism. And we can use these to exploit symmetries in reinforcement learning problems. So we make an explicit connection between the MDP homomorphism formalism and the extensive theory on equivariant networks. And I think that's nice because you can use one for the other now. So again, an MDP homomorphism is a map from the original MDP to a reduced MDP. In this case, it's a problem with symmetries and we fold over the symmetries. We create deep networks that are constrained by MDP homomorphisms and they enforce us to be equivariant to the inputs in terms of the output. So if we flip the input state, then we permute the output policy. We also introduce a new method that we call the symmetrizer that allows you to automatically construct equivariant network weights. I'm not going to go into that today, but I think it's nice because in reinforcement learning, the symmetries tend to change based on which problem you're looking at. So if you want to use this stuff in reinforcement learning, maybe you don't want to sit down and derive the constraints by hand every time. So the code for this is online. Oh, do you have a question? Oh, okay, good. I'm glad it's interesting. Right, so if you want to use this, then the code's online for the other stuff of the paper, the code's also online. And for the previous paper, the code's also online. So if you're into that, you can have a look. You can find it on my website. Right, so we evaluate these MDP homomorphic networks on a bunch of different reinforcement learning problems that exhibit such symmetries. So what we do is we use a normal model-free approach, except that the neural network in the middle is now an MDP homomorphic or equivariant network. So we evaluate on Quark-Pol, on a grid world with 90-degree rotation symmetry, and on POM. And here higher is better on the y-axis because it's the average return, which was the thing we're trying to maximize. And on the x-axis is the number of time steps that we spend in the environment. So the fewer time steps, the better, because it means you've used less data, basically. And the green graph here are the equivariant networks. The red ones are the sort of standard networks, which is an MLP for Quark-Pol, and a standard convolutional network for the other two. And you can see that it helps us be more data efficient if we exploit symmetries that we know are in the data. We also compared to different forms of data augmentation for POM, and we show that this definitely helps because you're still somewhat exploiting the symmetry in the problem, but it doesn't help as much as enforcing it. One caveat here, if your problem does not have these symmetries, you should probably not use this. Why? Because you're essentially constraining yourself to only the class of symmetric policies. So if the optimal policy for your problem is an asymmetric one, you would exclude the optimal policy. But if you do know that you have symmetries, then it can definitely help. Equivariant synonym, yes, exactly. Right, so to wrap this one up, we need fewer interactions to obtain good policies if we use MDP homomorphic networks or equivariant networks, basically. They're useful in reinforcement learning problems that exhibit group symmetry. And we also introduce a symmetrizer that automatically constructs equivariant layers. If you want more details, just please have a look at the paper. The code's also online. So I think we've only scratched the surface of what we can do here. I think, especially in reinforcement learning, which is extremely data hungry, methods such as I mean, group equivariance, but also other types of invariances, equivariances, or exploiting the geometry of the problem can be super effective. Just because the problem is so difficult that any prior knowledge that you put in can help you. So I think some things that I would definitely be interested in looking at are, for example, putting sort of group structured networks in self-supervised learning. So we're trying to find, I don't know, symmetric representations in some way. What if we have equivariance that is not group structured? So let's say you're driving along a road and suddenly it starts snowing. Maybe it doesn't really matter which road you're on, but if it's snowing, you always want to drive more slowly because the road gets slippery. Another thing that I think is interesting is looking at, for example, rotational symmetry in vectored MDPs. So for example, you have multiple objects that interact with each other. How can you exploit those? What can you do when you have partial observability? So you need to be symmetric over entire history. What if you have multiple agents? What if you know there's a symmetry you want to exploit, but it's very hard to define? Maybe you want to learn it. Maybe you want to exploit a symmetry that's only approximate. So it's not exact, but it's kind of there. So you kind of want to, to use that information. I think those are all super interesting research directions. So to wrap up the whole presentation, invariances and equivariance in markov decision processes can help you improve data efficiency and also help you learn representations from model-based RL. These are all ways of encoding prior knowledge into neural networks. There are many open challenges, and I think there's a lot of work to be done in this space. So if you're interested, definitely hit me up, either email or Twitter, or I don't know, have a look at my website. Thank you for listening. I see there's a question in the chat. In model-based RL, the learned model will not be perfect. To deal with this, there is some work that uses model uncertainty estimate to know where the model is not sure about its prediction. How can you deal with this when you use equivariant networks with model-based RL? I think you can kind of do the same thing, but now your uncertainty is sort of shared between the different symmetries of the state action space. So maybe you're uncertain about the specific state action pair. Now you would also be uncertain about the symmetric state action pair. And if you reduce your uncertainty on one part of the symmetry, then you also reduce your uncertainty about the other part. That's off the cuff what I think you would do.
Okay, I have a question. I think on the first slide, you showed on the equivariance and invariance. So let's say if you apply some transformation on a function, do we necessarily want to preserve the distance between the functions in the latent space? So like I think in that diagram you had some dotted lines. So do we necessarily want the dotted lines to be the same? Or,
no, not. I would say no.
Yeah, or we are okay provided at least we don't have overlapping functions there. Yeah.
Yeah, so I think what's important if you have a group structured equivariance, that G and G prime are maybe different representations of the same group element, but that doesn't necessarily mean that they have to have kind of the same distance, I think.
Okay. All right. Thank you. And one other thing is, are there specific kind of problems we are interested in, specific kind of symmetries in this case? So initially I was thinking that for graph neural networks, for instance, you want to model some complex environment, and that would be kind of your learning process for the model. But in this case, looks like we are taking a slightly maybe different turn, because we are only using geometric deep learning as a proxy to learn some symmetries that would help us to be more data efficient. So in cases where we are not learning the model itself, like the model free, do these techniques still apply?
Yes, so actually the second paper that I presented is a model-free approach. So the only prior knowledge that we put in is the knowledge of the symmetries. We're not actually learning a model of the environment.
Okay. Yeah, I think there's one more question in the chat.
All right. What will happen if we apply it to continuous environment without discretizing? Does the in and equivariance assumption still hold and is helpful? It depends. So if you want to use value iteration out of the box, you got to do some discretization. So if you don't do that, then you can't really use that approach, I would say. I think in continuous environments, the invariance and equivariance definitely still helps, but you have a symmetry over continuous states. So cardpole, for example, has a continuous state space, and the symmetry there, if you have a vector representation of the problem, if you flip over the vertical axis, that means you just multiply everything by -1. That's just the way it's represented in the environment. So for continuous places, this still helps. Does that answer your question?
Yeah, it helps. You mean only the group action will change here, right?
Yeah, exactly. So you can still apply discrete symmetries to continuous problems.
And still the efficiency will hold. I mean, the efficiency will still be the same in that scenario?
Yeah, so it depends. So are you talking about the model-based reinforcement learning or the MVP homomorphic network?
No, the other one.
Yeah, okay. Yeah, the MVP homomorphic network. Yeah. So there we also tested on cardpole, which is continuous problem. So I mean, the state space is of course continuous, but you can still sort of fold it in half, even though it's continuous.
Okay, so there's another one by Rami.
How can we scale that to high-dimensional problems where state action symmetries are complex or not clear? Nice question. Are there specific problems you're thinking about? Okay, so yeah, okay, like walking rope. Yeah, that's a tough one, I think. So you can definitely do it. So if you have, for example, a robotic locomotion task, or you're looking at Mujoko, then you definitely have the symmetries over the, let's say you cut the robot in half, then the left and right limbs are kind of mirrored versions of each other. You can definitely do it, but it's a lot harder to specify the symmetries because you got to mess around with your quaternions and stuff. I think what you need is a good engineer, and then you can definitely still do it. If the symmetries are just things that you have no way of knowing, then you end up in the point where you need to think about how you can learn the symmetries, which is, I think, still an open problem. Yeah, no worries. I think it's, oh, sorry, let me read the question. How about the applicability of this in real world physical systems? I think people actually use stuff like this in robotics where they, for example, when they build controllers for robotic limbs, they don't make a new one from scratch for every, for the left and right leg, right? They would probably also mirror the version of it. So the question if you can use this deep reinforcement learning in such systems, I think is that's a good question. I haven't done much robotics, so it's hard to answer. But I think in those cases you could still get some gain from exploiting the symmetries in the system.
Okay, I have maybe one naive question. So
okay.
can we create symmetries? Can we induce them? So we could maybe say that we have a network that is trying to create certain sort of symmetries in order to make our learning robust to other maybe unseen symmetries. Is it possible that way?
Interesting. Do you have an example?
No, not really.
Okay, so so are you thinking of enforcing symmetry, for example, in the learned free presentations, even if it's not necessarily there in the original problem?
Yes, instead of learning pre-existing symmetries, can we kind of create them to to kind of create some robustness in our learning model, perhaps?
It's a question I've been thinking about too. I think it would be super cool if you could say like, I don't know if you would necessarily call that creating the symmetries as much as saying, okay, if we want to be robust to certain transformations, then maybe the things that we care about in our problem are kind of invariant to those, right? So if you would say, I want to build in that I don't care about color, for example, then maybe the problem we care about is already invariant to color, but just not the way it's specified when we get the data. Does that answer your question?
Yeah, it gives me a lot of ideas. I don't know. I can't think of any answer to the question, so I don't know if it answers the question, but it gives me a lot of ideas.
Well, if you come up with a better answer, then I would love to hear it.
Yeah, right. Thanks. Yes. Does anyone has a question? Okay. Okay, looks like there's no more questions.
All right.
So yeah, thank you very much, Elise. I think
Yeah,
a lot of okay. I think there's one from Rami. Sorry.
oh,
Yeah.
are we using only visually clear symmetries like the left-right side of a robot? How about symmetries in hidden state action space, position velocity? I mean, you can do it. You can build as long as you can build a representation of the group that acts on this space, then you can build a network that exploits this symmetry. So it's definitely possible. It might take you might have to know your data well and be a good engineer to make it work, but it's definitely possible. Yeah, you're welcome. No worries.
Okay, so also in multi-agent systems, could we kind of use this kind of ideas to learn similar actions by similar agents in that sense? So so instead of having to learn what every agent is capable of doing in a particular situation, to rather look out for these symmetries to aid their interaction process.
Yeah, definitely. So there's a lot of work on permutation invariance and equivariance in multi-agent systems, where you kind of say, okay, if all my agents have kind of similar roles, then we can kind of exchange the parameters that they use. So if you learn something in this agent, then this agent can probably also take the same action in a similar situation. So there's a lot of work on that. Rotational symmetry, for example, I think that's maybe next.
Okay, so I mean, if you look what you just said, where you have agents who could be randomly permuted, and we know sort of their capabilities from these symmetries, can we also still maintain certain unique capabilities for each of these systems, not just the permutation? If you permute them, then you probably have the whole transfer of similarities or kind of their capabilities. But if you kind of have these agents, they have their own properties, certain things they can do, but there are some actions that are maybe invariant for these set of groups. So in that case, would permutation invariance really work?
So do you have an example of a system where you would want this?
So like you have maybe two agents, and this one have some physical similarities, but they choose to do the same things at the same time. Right. Yeah. So if you talk about the permutation, then it could be like we maybe exchange one for the other. We randomly maybe permute their states at some point. Yeah, but that would be like a full transfer of their capabilities, right? All properties belonging to them. So can we maybe learn about certain physical properties and not others to maintain others in that sense? So I'm just thinking permutation invariance might not be enough in this context.
Sorry, I missed the last part of it. So permutation invariance is not enough in the context. So you have two agents. They have not the same physical system, but they have comparable actions.
Yes.
Okay. So correct me if I'm misunderstanding your question, but I would think that you could maybe find a shared representation space for both agents' action spaces. So let's say you have a robot arm that has to pick up a cup, and then you have a regular bipedal robot that also has to pick up a cup. Maybe you want to find a shared representation space where they both have some kind of action called pick up cup, and depending on what the physicality is of the robot, you can exchange the actions.
Oh, okay. So that is learning like shared representations for them instead.
Yeah.
Okay.
Yeah, I mean that would be my first guess, if I understand you correctly.
Yeah. Okay. Yeah. I think I'll follow up on that. I will read a bit more about that. Thank you.
Okay. Sure.
So let me ask a question.
How about multitask reinforcement learning, same environment, different task? Right. So there's some work on if you learn a model that has a separate transition and reward function, then you can keep your transition function and just throw out the reward function and, for example, learn a new reward function or insert a new reward function if your goal changes. This can like goal conditioned reinforcement learning.
Ram, is it okay?
Okay.
Yeah. Okay, Elise, thank you very much for your time. We really appreciate it. And thank you, Taco, for inviting Elise.
Yeah, thanks for having me.
Yeah, and many of us are very interested in this and we'll definitely follow up. We would maybe reach out to you at some point.
Oh, yeah, please do. Always love hearing interested people. Yeah, definitely.
So thank you very much, Elise.
All right. Have a nice day.
Yeah, you too. Bye.
Bye-bye.